All right, so this is Mullins Virtual SI. We have our review session tomorrow. So in replacement of a session that was originally supposed to be tomorrow, I'm going to make this video explaining the acids and base worksheets. All right, so for these molecules, we just have to give a pKa value, and it indicates the most acidic hydrogen. That's how it's going to be like on the exam at 2. So here, this is basically just asking what's the pKa of an alcohol. We've seen before on the Quizlet and in the book on table 4.5 that the pKa of an alcohol is going to be 16. Just because we have these extra methyl groups does not mean the pKa is going to be any different. So the pKa is going to be around 16. For here, this is a carboxylic acid functional group, meaning that the pKa for the carboxylic acid will be 5. Acetic acid is the one given in the book, actually. HF, so HF is one of those, 13 now we have to know. pKa is going to be 3 for this one. For this one down here, the C to C triple bond, we see that in our table, or on the Quizlet, we know that an alkyne, which is this functional group, the carbon-to-carbon triple bond, the hydrogens coming off an alkyne are going to be pKa 25. So that's that pKa. Here's an amine functional group. This is given in the table or in the Quizlet. It's given as NH3. However, this carbon attached to it, basically, instead of this extra hydrogen that is typically present in ammonia, which is NH3, instead we just have this ethyl group. And that actually doesn't change the acidity too much. So we can assume here pKa is just going to be 38 because the pKa of ammonia is also 38. All right, number 2. So for these reactions, we have to calculate KEQ. So if you remember, we have a process for calculating KEQ. That process involves, number 1, what we have to do is we have to identify the acid on both sides. We have to take the difference between the pKa's, and then we have to put that in exponent form based on what we think is going to be favorable. So for these two, protonated amine, you saw this in the table as NH4. In this case, right, the carbon isn't going to change the reactivity. The pKa of an NH4 group is going to be pKa is equal to 9. Over here, though, right, you may be tempted to think, how did I know this was the acid? First of all, it's losing its proton in the forward reaction. So here it has 3 protons. Here it has 2 protons, so that means it's losing. That means this alcohol right here has to be gaining that proton, and indeed it does in the products. For this protonated alcohol, so we saw in the table for H3O+, the pK of an H3O+ is going to be 2. Negative 2. That means because this carbon does not influence the reactivity that much, the pK is also going to be negative 2. So all we have to do now, we have to take the difference between both sides. So the difference in pKa is going to be 11. Now we have to decide, is this going uphill or is it going downhill? So at this point, we're left with 2 options for the KEQ. It can either be 10 to the 11th or 10 to the negative 11th. If it's 10 to the 11th, that means the reaction's going downhill and the products are more stable. If it's 10 to the negative 11, that means we're going uphill. In this case, right, the pKa that is lower, aka the stronger acid, is on the right side. That means that the equilibrium is going to favor the left side, right? It's hard to give this alcohol a proton and have it be happy. And therefore, the KEQ for this first reaction is going to be 10 to the negative 11. There we go. Now we just have to draw an arrow pushing mechanism for the forward reaction, and for this we just take away one of these protons from the protonated amine, and then these electrons just go back to the nitrogen. And we can do our counting here. We see that lone pair appears on the nitrogen, and then these hydrogens appear on the oxygen. So that's it. We did both of those things. Now we can focus on the second problem, right? calculating the KEQ again. We have to identify the acids and the bases on both sides. Here, the carboxylic acid is losing a proton. And that means, in this case, this is going to be the acid on this side. In this case, right, this is going to be the base for the first reaction, meaning that this is going to be the conjugate acid. So this is the acid for the reverse reaction, right? So there we go. So this is going to be our acid too. The pK of a carboxylic acid is 5. And the pK of an alkyne is 25, just like we listed above. We calculate the difference in the pKa's. That's going to be, in this case, 25 minus 5, which is 20. Now we need to decide, is this reaction going uphill 25, or uphill 20 points, or is it going downhill? So we can either have it going downhill, or we can have it going uphill. In this case, right, our stronger acid is over here. It's the acetic acid. The lower pKa means it's a stronger acid. And that means that the reaction will be favored forward, meaning the KEQ is positive 20. Got it. One thing I wanted to point out that I noticed up here, the reason why the difference is 11 is because this goes into the negative region. If you go into the negative region, the difference between them is still 11 values. So like you can go -2, -1, 0, and then you have 9 values. That's a total of 11 values. All right, so that should be good for this one. Definitely expect to solve something like this on the exam. In this case, these are hard problems. We have to predict which one's more acidic and explain why. If you have been following along, you know, how do we solve these problems? If we were in person, I would say, how do we solve these problems? The way we do that is we draw the conjugate base. So the first thing we always have to do when we're looking at a problem like this, we want to solve for the conjugate base. And if you don't do that, you will get points taken off on the exam. That's how you are supposed to solve them. You're supposed to draw the conjugate base and then talk about how is the conjugate base more or less stable depending on certain factors. If you're asking yourself, what is this question testing us on in this case, we can go through our list, right? We can talk about, is it the atom in terms of size and electronegativity? In this case, what's the atom that has the negative charge? It's carbon on both, so atom is not going to be a factor. Is resonance possible, right? So we can think resonance. Is resonance possible here? In fact, it is not. If you try to draw a resonance structure here, you'd get a quadruple bond, which we never see. And here, if you try to do that, this carbon has a hydrogen, so you can't do that either. That would have a 5-bonded carbon. So resonance is out. You can't do resonance. We can do induction, perhaps. But in this case, we don't see any electronegative atoms, so that's out as well. The only one that's left is hybridization. And that is obviously the correct thing that this question is testing us on. So in this case, it's sp. In this case, it's an sp2 carbon. When you deprotonate a acid, the hybridization stays the same for the atom that had the hydrogen was attached to, since you're just getting a lone pair anyway. So in this case, we basically just have to ask ourselves, which conjugate base is more stable? Is it the sp or the sp2 hybridized carbon with a negative charge? You may remember s orbitals. So s orbitals are, the s stands for small and spherical. So in this case, this has 50% s character, right? If it's hybridized sp, that means 50% of the hybrid orbitals are going to be s character. In this case, it's going to be 33% s character. And that means that here, right, I'll just go ahead and spoil the question. This is the more stable conjugate base. And that's because the sp hybridized orbitals are closer to the nucleus. And negative charges like to be stabilized by that positively charged nucleus. If the left side is the more stable conjugate base, that means that this species here must be more willing to give up its proton compared to this species over here. Got it. Last problem on the worksheets. We want to predict which one's more acidic here and why. What is the first step to solving this problem? Of course, it's going to be to draw the conjugate base out. So here we have our conjugate bases for these species. Now we need to go through the list and ask ourselves what factors are going to be playing a factor here. So O stands for hybridization, if you remember correctly. So we can go through this list, right? Is the atom mattering in terms of both size and electronegativity? Carbon and sulfur actually have pretty similar electronegativities. However, sulfur has a much larger size, so we'll put this as a winner towards that side. We need to ask ourselves, is resonance possible? It is not possible over here since this carbon has 4 bonds already, so it cannot form a double bond. In this case, though, right, we can push this carbon oxygen double bond up, and that will form a resonance structure. And moreover, right, now that we've done this, this oxygen actually has electronegativity advantage over the sulfur, even though it's smaller. However, I'm just going to put resonance for simplicity, since size wins over electronegativity of the atom anyway. We can also ask ourselves, is induction possible? In this case, for the left side, right, we have these 3 fluorine-containing groups over here. And that means that induction is on our side here, right? This induction effect from these fluorines is taking away electron density away from this oxygen. That's going to stabilize the conjugate base. Is induction possible for the right molecule? We have no electronegative atoms like fluorine, chlorine, etc. So this is not going to be possible for induction over here. We can talk about hybridization a little bit. You can ask yourself, what's the hybridization of the oxygen? Here, and you would actually discover, since it has resonance, you'd see it has sp2. The sulfur has sp3, hybridized orbitals. So at least slightly, not too much. Sulfur, the left molecule also wins in terms of hybridization too. So this means that there are 3 factors, right? 3 factors going towards the left side being the more acidic molecule and the more stable conjugate base. All right. So that's pretty much it. You should expect kind of all these types of acid-base problems for exam 1. Thanks for watching.